Welcome students to part 2 of section 7.7, Approximate Integration. In this video segment, we will look at error estimates, estimating the error involved in using approximate integration techniques to estimate integrals. Okay, so a little bit of a recap of what we've done so far numerically. So far, we're considering, and we'll continue to consider the same integral through most of our lecture. At the very end of the lecture, I'll take a look at a short example involving a different integral. But so far, we're considering the integral of 1 over x with respect to x from 1 to 2, whose value we know from previous sections is the natural logarithm of 2. Okay, so what we did in the last video segment is we used 4 different approximation techniques to estimate the value of this integral. We used the right-hand rule with 5 subintervals, the midpoint rule and trapezoid rule also with 5 subintervals, and Simpson's rule with 4 subintervals. I mentioned that we rarely use the right or left-hand approximations because they are grossly inaccurate compared to the other 3 methods in this section. The midpoint rule is very accurate. The trapezoid rule is about half as accurate, but sometimes we need to use the trapezoid rule over the midpoint rule because we don't have access to the y values at the midpoints within the subintervals. So there's a trade-off there. Then we looked lastly at Simpson's rule, which is much more accurate than even the midpoint rule. And we used n equals 4 subintervals to estimate the integral. We used 4 because Simpson's rule, unlike the other rules in this section, or the other methods in this section, Simpson's rule requires an even number of subintervals. And I listed there the actual value of the integral to, let's see, 10 decimal places. And again, that integral equals the natural log of 2. I accessed it just by using my calculator. I just pushed ln2 and enter. Okay, so let's dig into estimating error. Just to remind you, the formulas are very, very easy to use, extremely easy to use, especially since we have our calculators and machine technology to do the computations for us. On the other hand, error estimation is extremely difficult in general. There's a whole branch of mathematics called approximation theory, and certain mathematicians spend their entire lives studying approximations to quantities in mathematics and keeping track of getting a handle on errors involved in these estimations or approximations. So let's go back and define what we mean by error. We're going to use E, capital E, to represent error. Okay, so E in our course represents error, and we're going to define error as the true value of whatever quantity we're estimating minus the estimate or the approximation. Okay, so why not the other way around? That's purely arbitrary. So we're going to define for our particular section the error involved is the integral, the actual value of the integral we're estimating minus the estimate. The estimate would be either the estimate for the right-hand rule, left-hand rule, trapezoid, midpoint, or Simpson's rules. Minus the estimate. Okay, in this course, we're not so much concerned with the error, but something called the magnitude of the error, which is not a real fancy idea. We're interested not so much in error, but the absolute value of error. So this is called the magnitude of the error. And we lose something when we look at the magnitude of error rather than the actual error. The actual error, if the actual error turns out to be positive, then we know that our estimate is an underestimate. because the true value would be more than our estimate. If the error was negative, then the estimate is too much. It's an overestimate of our true value. So the magnitude of error hides that completely, and that's a little bit of a trade-off. Okay, so I would like to put in order from most accurate to least accurate or actually I'd like to list the magnitudes of error for the three methods from smallest to largest. The Simpson's rule is the most accurate, so the magnitude of the error using Simpson's rule is less than or equal to the magnitude of the error using the midpoint formula. Notice that it's not strictly less than, it could possibly be equal to. So there's some functions that when we integrate using midpoint or Simpson's rule, we get the same error. In most cases, it's not true. In most cases, we have the strict inequality. So the magnitude of the error using midpoint's rule is then less than or equal to the magnitude of the error using the trapezoid's rule. So here's how we ordered the three magnitudes of error. So our next task then is to start looking at the formulas, or some formulas for these error magnitudes, and use them primarily in our same integral from 1 to 2 of 1 over x dx. So let's take a look at these formulas. Okay, so here are our first error estimates. They're complicated things to look at. There looks like there are a lot of variables floating around, but you'll get used to them quickly. Let's take a look at them and kind of analyze what they're saying. The first magnitude of error, the magnitude of error, the absolute value of error using trapezoid rule, is less than or equal to. Now, a common way to state less than or equal to is to say is no bigger than. So if something is less than or equal to something else, then the first thing is no bigger than the second thing. So this is saying that the magnitude of error using trapezoid rule is no bigger than this fraction k times b minus a cubed over 12n squared. Excuse me, there's my dog again. I have a border collie. He barks at skateboarders going by, so I apologize for that. Last session, a student was studying the video material at about 2 in the morning, and she left a comment below on one of my videos after my dog screeched out one of his ear-shattering barks that it scared the hell out of her. Poor thing. She was studying all alone in the middle of the night. So anyways, such is life, and I don't think I'll edit the barking. I'll just leave it for posterity. Anyways, so the magnitude of the error. Back to the right hand side. These error estimates look very complicated, but really there's only one thing that's new in the right-hand sides of these things. We have k, we have b, we have a, we have n. The a and the b in these estimates are just the upper and lower limits of integration, and the n is just the number of subintervals that we're choosing to estimate our error. Okay, the k is the new thing. But before we get to the k, take a look at these formulas. Remember, the larger the number of subintervals, the more subintervals we use, the more accuracy we get. If you think about that with respect to the definition of the integral that I was giving you in the last video segment, using rectangles to estimate the the area underneath the curve. Well, you squeeze more and more and more rectangles in, the error diminishes. So how do we get the exact value of the limit? Remember, we let n approach infinity. Well, look what happens on the right-hand side if we let n approach infinity. As n approaches infinity, those fractions approach 0, and so our maximum error also approaches 0. So it makes sense that we're going to have n in the denominator of these error estimates. Okay, and again, the a and the b are just the lower and upper limits of integration. The k, that constant k is what makes the error estimates difficult. In fact, and I don't have a soft way to put this, that k and the corresponding k in the error estimate for Simpson's rule that's coming up is probably in the top 3 to 5 things in the course that are the most difficult. By far, the most difficult part of the course is coming up in chapter 11 when we talk about series. But a really close second or third to those things is actually finding this constant k. So what is this constant k? So I'll tell you. So the constant k is such that, where k is a number, is such that, so oops, I can't spell such that, is such that, I'll try to fix it, the absolute value of the second derivative of the function that you're integrating is no bigger than that k for all x in the interval from a to b. That's the interval over which we're integrating. Now we have to look very carefully at what that means, because it's going to be likely going to be the hardest part of this this whole discussion of approximate integration is that constant k. So let's take a look at what that constant k represents graphically. So here's I'm attempting to graph a function here. I think I'll do it off camera. So what you see on your screen in the lower left is the second derivative of a particular function we're integrating. Not the function, not its first derivative, but assume we have the second derivative graphed. And you notice that the second derivative I have pictured there has a minimum value of -5 and a maximum value of 3. Well, in this case, it's a common mistake for students to say then, oh, the second derivative is always less than 3. And that's true. The second derivative is always less than or equal to 3. But that's not a viable value for k. Okay, k isn't obtained by finding the maximum value of the second derivative. K considers the absolute value of the second derivative, the absolute value of the second derivative. So again, take a quick look at the function on the lower left. If that's the second derivative. Now the function right next to it that I've graphed is the absolute value of the second derivative. What does the absolute value do to the negative parts of a graph? What do you have to remember that? What the absolute value does is it brings the negative parts of the graph up across the x-axis. Okay, so let me ask you this. If you can get this, you're on your way to understanding k. It's still a little rough finding it, but you're on your way to understand it, what it is. So what would k be? What would the best possible value for k actually be? And if you're thinking 5, then you're correct. Then you're absolutely correct, no pun intended. Now the thing is, in my drawing, that 5, that's the best possible value of k, but we don't have to choose that value. In fact, many times we can't get that best value of k. We have to settle for any value of k that we can find. Now that may not make sense right away, what I just said. So I want to draw that picture once again, and then talk about a little bit more about what I'm mean by the best value of k. So here's my absolute value of second derivative again, and I'm looking for any number. Now it's important the way I'm stating this. I'm looking for any number so that the absolute value of the second derivative is less than or equal to that k. k equals 5, that's the best value. This is the best possible value of k. But k equals 6 would work. Is the absolute value of the second derivative less than or equal to 6? Yes. How about 7? Yes. How about 10,000? Yes. How about 4? No. The best value of k is 5. Sometimes, though, in fact, very often, we have to settle for, because k is so very difficult to find, we have to settle for an estimate for the best value of k. And every time we settle for an estimate of the best value of k, we make our error estimates worse. So this error estimation business is very difficult. It's very difficult to get a really good estimate of error. And again, some mathematicians spend their entire lives studying how to do this. Okay, and this is just scratching the surface of error estimation. Okay. So let's dig in. Let's take a look at estimating some error based on the integral approximations that we were working on in the previous section. So, for example, estimate the magnitude of error in using the trapezoid rule and the midpoint rule. Trapezoid rule and the midpoint rule to approximate the integral from 1 to 2 of 1 over x dx. Okay, well, we go back to our formulas. The magnitude of the error involved using trapezoid rule is no bigger than that bizarre k times b minus a cubed over 12 and squared. We'll start with the trapezoid rule. Okay, so we know that the magnitude of error then, what is no bigger than, well, remember when we were estimating this integral, we had n equals 5. So I should put in my original example with n equals 5. As we did last time, we used n equals 5. So it's no bigger than, the magnitude of the error is no bigger than k times b, the right-hand limit of integration, 2 minus a, left-hand limit, cubed, over 12 times 5 squared. So as soon as I can figure out k, I can put that k into the right-hand side, and I get an estimate to the maximum value of my magnitude of the error. Okay, so we need k. There's no getting around that. Let's get k. Remember, k is some number, and there are many different possible values for k. Well, so k is such that the absolute value of the second derivative of my function, the function I'm integrating is 1 over x, so the second derivative of 1 over x is no bigger than that number k within the interval from 1 to 2. Okay, so let's do this. Let's see if we can find that. We're going to need two derivatives. Well, the function is 1 over x, or x to the minus 1. So the first derivative is minus 1 x to the negative 2. The second derivative brings down the negative 2, becomes positive 2 x to the negative 3. So the absolute value of the second derivative, not the second derivative itself. A lot of students have made a mistake in the 30 years I've been teaching this course. In 3 decades I've been teaching this course, I've seen students make the same mistake over and over and over again, and that's to try to find k based on the second derivative. It's the absolute value of the second derivative, so be careful. So the absolute value of 2 over x cubed. Okay, now remember that we're considering the interval from 1 to 2. We're integrating over the interval from 1 to 2. And in that interval, there's something really nice happening with x. Over the interval from 1 to 2, x is positive. So if x is positive, 2 over x cubed is positive. So we can eliminate the absolute values on the right-hand side of this last inequality. So the absolute value of our second derivative is no bigger than 2 over x cubed on the interval from 1 to 2. Okay? So we need that value, a value for k, Now, look on the right-hand side. 2 over x cubed is a function that we're supposed to know how to graph. We should know this from pre-calc. 2 over x cubed looks like this. I'm graphing it on the right here. 2 over x cubed looks like this, and it continues on. It has a vertical asymptote, but between in the interval between 1 and 2, it's a decreasing function. This is very, very important. On the interval from 1 to 2, it's a decreasing function. So if a function decreases, then its maximum value has to occur on the left-hand endpoint. If something's getting smaller, then its maximum value occurs in the left-hand endpoint. So the maximum value of 2 over x cubed is no bigger than, the 2 over x cubed is no bigger than 2 over 1 cubed. I'm substituting the left-hand endpoint because that's where this decreasing function has its maximum value. And that's 2. And that's k. Okay, so our k is 2. Our k is 2, and we can go ahead and finish up our problem. The problem says then that the maximum value of the error using trapezoid rule is no bigger than k 2 times b minus a, 2 minus 1 cubed over 12 times 5 squared. Okay, and this number is 0.006666, and 6 repeats. Okay, now let's take a look at what this means. Think about the definition of error. Think about the definition of error. The definition says you're taking your true value, the actual value of the integral, minus whatever your estimate is. And when you subtract those two things, you get your error. And look what happens when we subtract those two things. When we subtract those two things, we are guaranteed to have zeros in the first two decimal places of that difference. That means the first two decimal places are approximately correct. This is saying that we have approximately 2 decimal places of accuracy. Okay. Now let's go back to our the beginning of the video. So watch your eyes here. I'm gonna scroll way back up to the very beginning. Concentrate now on the trapezoid rule that we looked at. That's T5. That's the estimate compared with the true value. The trapezoid rule and the true value agreed with each other to 2 decimal places of accuracy. So this error estimate is bearing true. It's working out for us. And the reason why it's working out for us so well is we found a really good value of k. Okay, so let's take a look at using the error estimate for the midpoint rule now. Okay, so watch your eyes again. I'm gonna scroll way down. The midpoint rule I mentioned last time is in some sense twice as accurate as the trapezoid rule, and here's why we say that. The magnitude of error using trapezoid rule is no bigger than k times b minus a cubed over 12 and squared. The magnitude of the error using the midpoint rule looks very similar. There's only one difference. K times b minus a cubed over 24n squared. Now look at the denominator in that maximum error. The denominator in the maximum error of midpoint rule is twice as big. That makes the error, the maximum error, twice as small for the midpoint rule than the trapezoid rule. Now be careful, that doesn't mean that for every problem the error in the midpoint is going to be twice as small as the error for the trapezoid rule. These are maximum error estimates. It could turn out that using both these methods we get exactly the same number of decimal places of accuracy, but generally the midpoint rule is considered, because the maximum error, the maximum magnitude of error has 24 in the denominator rather than half of that 12, is considered to be twice as accurate in that sense. Okay. If that doesn't make sense, it's not too important to digest that right away. Okay, so let's just move on with our maximum error for the midpoint rule. We figured out maximum error for trapezoid rule is about 0.006 repeating. So with the midpoint rule, let's do that for our integral. The maximum error using the midpoint rule is no bigger than k. The k is the same for midpoint rule as it is for trapezoid rule, so it's 2. And the b and the a are still the upper and lower limits of integration respectively. I have 24 instead of 12 in this estimate, and the same 5 that I had in the magnitude of error for trapezoid rule. And this value is 0.003 repeats. That's half of the maximum error that I had in the trapezoid rule. Okay, in the trapezoid rule I had maximum error no bigger than 0.0 and then 66666, etc. Now I have maximum error less than 0.003, etc., etc. But I still only have 2 zeros in this is the first 2 decimal places, so I'm still only getting an approximate 2 decimal places of accuracy, even though my rule is generally twice as accurate than the trapezoid rule. Okay, so we don't guarantee more decimal places, but in general we got a better rule by 2 times as much for midpoint rule. Okay, so now let's take a look at the magnitude of the error using Simpson's rule. We get a different formula and a different kind of k. Okay. So in the first 2 lines you see on your screen, those are once again the 2 error estimates for trapezoid rule and midpoint rule, where k is based on the absolute value of the second derivative. The absolute value of the second derivative is less than or equal to k. Now here's the error estimate for Simpson's rule. The error estimate for Simpson's rule says that Simpson's rule, the magnitude of the error is no bigger than k, not the same k. Some authors use a different symbol. Our author still uses the same symbol, so we'll be consistent. But we'll have to understand that k is different. So the magnitude of the error is no bigger than k times b minus a to the 5th, not to the 3rd anymore. Now look what we're dividing by. 180. And that's not really what makes the error so small. It's the fact that we're multiplying also by n to the 4th in the denominator. So the error estimates for trapezoid and midpoint rule have n squared in the denominator. When you take the number of intervals, sub-intervals, say 5 or 10 or whatever, and square them, you get a bigger number. But if you take those same number of sub-intervals and raise them to the 4th, you get a much bigger number, making that whole right-hand side much smaller. So the bottom line is the Simpson's rule. The error in the magnitude of the error in Simpson's rule is much less than even the midpoint rule by a whole lot, by a tremendous amount. So let's do this. Let's do this the same thing we did in the previous example with our integral, but with Simpson's rule. Here's the statement of the problem. Estimate the magnitude of error in using Simpson's rule to approximate the integral, the same integral, the integral from 1 to 2, 1 over x dx with n equals 4. We've decreased n, and when you decrease the number of subintervals, generally you increase the error. So we're decreasing n from 5 to 4 because we need an even number, and I decided to come down one number just to make a point that the point that Simpson's rule is so much more accurate that even when we come down in n, we still get better accuracy generally. So let's do this. The magnitude of the error using Simpson's rule then is no bigger than k times b2 minus a1 2 minus 1 to the 5th over 180 times n4 to the 4th, n to the 4th power. Okay, so we need our value of k. K is, again, k is not the same value of k. K is such that the absolute value of the 4th derivative is no bigger than that k over the interval we're integrating, on the interval from 1 to 2. Okay, so let's pick up where we left off with that function and its derivatives. The function was 1 over x, is 1 over x, which is x to the negative 1. The first derivative, might as well do them all over, it's no big deal, is minus x to the minus 2. Second derivative is 2x to the minus 3. We keep going on the derivatives. Third derivative is minus 6x to the minus 4th. And finally, the 4th derivative. We put the order of derivative in parentheses in Arabic numerals after the 3rd prime. So it's 24x to the minus 5, or 24 over x to the 5th. Now, that 24 over x to the 5th, well, it's different than the function we got for the earlier value of k. It behaves exactly the same way over the interval from 1 to 2. In the interval from 1 to 2, now this is not to scale. I can make this a little better. In the interval from 1 to 2, this function is still decreasing. It's not going to be to good scale here, but that's okay. In x equals 1, the absolute value of my 4th derivative is 25. And of course, this is not to scale at all, so I apologize. And at 2, we have 25 over 2 to the 5th. Okay, now, did you catch my little problem there? Did you catch I fell for the same problem that I said that I've been noticing for 3 decades. I looked at the maximum value of the 4th derivative instead of the absolute value of the 4th derivative. In this case, there's no difference. But that's still a mistake to consider the absolute value of your 4th derivative and not the absolute value. Here's what I mean. The absolute value of the 4th derivative then is the absolute value of 25 over x to the 5th, but that's just 25 over x to the 5th because the interval over which we're integrating is a set of positive numbers. Okay, so this is on the interval from 1 to 2. So the absolute value of my fourth derivative then is no bigger than 25 over 1 to the fifth. Again, we choose the left-hand endpoint because this is a decreasing function. This absolute value of the fourth derivative is decreasing. If you have a decreasing function on an interval, its maximum value has to be on the left-hand endpoint. So our k value, the best possible value for k, is 20. Oops, there's another mistake. 24, and I'm sure a whole lot of you saw this. So before I see it popping up in the comments, and you can even put it in the comment if you want, I have to correct my mistake here. It's not 25, it's 24. I'm sorry. This is 24. Wherever we have a 20, I don't know why I put 25. I put 25. I saw it all over the place too before I caught my mistake. Well, I guess nobody's immune, huh? Okay, 24. Okay, so I hope I didn't throw you off too much with that 25. Okay, so our k, the best possible value for k is, and we found it in this case, is 24. Okay, so let's go ahead and finish off this error problem. So finally, the magnitude of error using Simpson's rule then is no bigger than k times b minus a to the fifth over 180 times n, 4 to the fourth. And this number is 0.00052083, etc. Now notice what that's telling us here. This is telling us that when we subtract the estimate from the true value and take the absolute value, there's agreement in the first three decimal places. So we have approximately 3 decimal places of accuracy. And again, watch your eyes, because I'm going to go all the way to the top of the lecture. I know this is going to go crazy with your eyes and stuff. Sorry. I guess I could have stopped the video. Oh well. Live and learn. Okay. Here is Simpson's rule with n equals 4. And notice that we have, with the true value, we have 3 decimal places of accuracy. And we have 3 decimal places of accuracy in our true value. Okay, 0.693. 0.693, we have agreement in 3 decimal places. Okay? Okay. Our next example, and I'm going to be a little dramatic here in kind of a good way. Our next example is probably one of the best examples that I've produced for you guys all session, for the whole session or semester. Okay, this example is going to illustrate real world STEM field mathematics stuff. Okay, so let's think about this for a second. When we feed in our calculator natural log of 2, we want to compute the natural log of 2. Your calculator is going to estimate this integral. This is how we compute the natural log of 2. So how does it do it? How does the calculator estimate the integral from 1 to 2 of 1 over x dx? Well, it most likely uses Simpson's rule or a similar, very accurate rule to do that. Well, how does it know? How does the calculator know, or how is it programmed to determine the number of subintervals that are necessary to get the, 8, 9, or 10 decimal places of accuracy? Well, this example illustrates how that's done. This is real world math going on in this problem. So here's the problem. Find the value of n, the number of subintervals, that ensures that the magnitude of error in approximating our integral, the natural log of 2, is less than, so that the magnitude of error is no bigger than 0.00001. And that 0.00001 is 10 to the negative 5th power. So you could translate this question into how many subintervals should I choose so that I get approximately 4 decimal places of accuracy? The graphing calculator would have more, twice as many decimal places of accuracy, but approximately 4 decimal places of accuracy. Okay, so I'm not looking at the actual estimation of the integral. I just want to know how big n should be so I get this kind of accuracy. So I want to see how big n should be for trapezoid rule, for midpoint rule, and for Simpson's rule. And we get very surprising results. So let's do this. So for A, oops, I don't want to do this in green. So for part A, the magnitude of the error using the trapezoid rule is no bigger than k times b minus a cubed over 12n squared. Or, now remember, the value of k we found was 2. This is from before. B minus a cubed over 12. And when we were computing the magnitude of error for trapezoid rule before, we knew n was 5. Now we don't know what n is. N is variable. Okay, so this value is 2 over 12n squared. 2 over 12n squared. And I need to choose n now. N is a variable, so that when I set this quantity less than 0.00001, that the inequality will be satisfied. So this is, that again, that's 10 to the negative 5th. So we solve this inequality for n. So let's solve that inequality. This says then that 1 over 6n squared is less than 10 to the negative 5th. I want to take the reciprocal of both sides. So this says that 6n squared is greater than 10 to the positive 5th. Divide both sides by 6. N squared is greater than 10 to the 5th over 6. Take the square root of both sides. You get n is greater than the square root of 10 to the 5th over 6. And I computed this number as 129.09, etc., etc., etc. So don't lose track of what we're looking for here. We want the error to be no bigger than 0.00001. I want 4 decimal places of accuracy. I'm going to have to choose n to get that 4 decimal places to be what value? And the answer is not 129.09. n has to be greater than this, and n can't be a fraction. It's a number of subintervals. So what's n have to be? 130. I'm going to need to choose 130 subintervals. Now there's a problem with that that's not showing up here. The more subintervals you choose, the more computations you're making, and the more computations you're making, the more additional error is incurred. Every time you add something to your estimate, you introduce more error, what called round-off error. Okay, let's not get into that too much. Okay, actually, let's not get into it at all. But we're going to need 130 computations. Okay, 130 subintervals. So now let's do the same thing with midpoint rule. Now remember, midpoint rule is supposed to be twice as accurate in some sense. So that means n needs to be less, or n is not now half of 130. No, that's not how that works. Okay, let me show you. The magnitude of the error for midpoint rule is no bigger than k times b minus a cubed over now 24. There's where that twice as accurate comes from. 24 is 2 times 12 in the previous denominator. Okay, well, that value of k is still 2, b is still 2, a is 1 cubed over 24n squared. Okay, and then we set that less than, not less than or equal to, just less than. We set that to be less than 10 to the negative fifth, the same 0.00001. 10 to the negative fifth. So we get 1 over 12 n squared is less than 10 to the negative fifth. Okay, I'm going to skip the steps here. The steps are the same as they were in the previous part. So n needs to be greater than 91.287 ... So I need to choose, since n has to be bigger than an integer bigger than this number, I need to choose n to be 92. That's a whole lot fewer subintervals. That's a whole lot fewer computations that are necessary than the trapezoid rule to get the same accuracy. Now the really surprising result. Let's do the same thing with Simpson's rule. The magnitude of the error using Simpson's rule is no bigger than the Simpson's rule constant. It's a different k than for midpoint or trapezoid. B minus a to the fifth over 180 n to the fourth. Now the value for k for Simpson's rule was, I made a mistake and said, remember I corrected my mistake, said 25. It's 24, 2 minus 1 to the fifth over 180 n to the fourth, and I set that to be less than 0.00001, or 10 to the negative fifth. Okay, now when we solve this for n, we get n that needs to be greater than 10.745 ... So I'm going to ask you to think about this. Now be careful. 50% of the time I get the wrong answer. What should I choose as the number of subintervals? If you thought 11, that's wrong. You want to give it another shot? It's Simpson's rule. Simpson's rule, n has to be what kind of number? So n will need to be 12. 12 computations, 12 subintervals, as opposed to 92 subintervals for midpoint rule, or n equals 130 for trapezoid rule. Simpson's rule rocks. It is an extremely accurate method of integral approximation. Okay, so for our last example, I'd like to give you an example that's going to help you with one or two difficult homework problems. And I chose to do an example that your author does for two reasons. One, it's a good example, and two, he makes a mistake. He makes the same mistake that I told you I've seen forever, and I made it tonight when in this video. I forgot the absolute value. Okay, so what I'm going to do is I'm going to look at an example of, and the example is just to find the magnitude of error using Simpson's rule, and the hardest part is the k. This is the real value or real reason for this example. The example is from your textbook on page 563. I hope I got that right. Yeah, I think it's right. This is example 7, part B. Part B. Okay. There's an error in the book. After 8 editions of the book, there's still an error there. Okay. I'm partially at fault there. I've used the textbook forever, and I've never reported the error. I've never reported it to the publisher, so apparently nobody else has either. Okay, so it turns out in part A of this problem, it turns out that in using Simpson's rule, with n equals 10, to estimate an integral, to estimate or approximate the integral from 0 to 1 of e to the x squared, we get, and there was no mistake on this part, we get s sub 10 is equal to 1.46261. Okay, so our problem, part B, is to estimate the magnitude of the error. So let's estimate the magnitude of the error using Simpson's rule with n equals 10. Okay, so remember that the magnitude of error using Simpson's rule is no bigger than the Simpson's rule constant k times b minus a to the 5th over 180 n to the 4th, where k is any constant such that, not any constant at all, but any constant that behaves like the absolute value of the 4th derivative of x is less than or equal to k on the interval over which we're integrating, and we're integrating from 0 to 1. Okay, well, I'm going to save you the tedious computation of finding the 4th derivative. You might want to actually practice with it, but that's all right. You'll have enough homework. So f of x is e to the x squared. Okay, after a whole bunch of algebra, and I verified that his derivative was 4th order derivative was correct. After a whole bunch of algebra, you end up getting 12 plus 48x squared plus 16x to the 4th. All that times e to the x squared. Okay. Now remember, we're not trying to find the biggest value of this function. We're trying to find essentially the biggest value, if we can, for the absolute value of this. Okay, so this is where he makes the mistake. He doesn't take the absolute value. He doesn't even mention it. Now, his answer was correct, but he got lucky. He got very lucky. The author got very lucky with this. X to the 4th, e to the x squared. And the reason he got lucky is, remember, we're on the interval from 0 to 1 along the x-axis. Look at this function. It's an ugly looking function. It's not that bad, but it's a little ugly. On this interval, there are only pluses in the function. The exponents are always even numbers. E to anything is always positive. This function's already positive. This function is already positive on the interval between 0 and 1. again, he got lucky. He didn't consider the absolute value at all, but generally this isn't true that you can just dump the absolute values. So now let's find k. For this problem, graphing the right-hand side is not a good idea. The graph of the right-hand side is very complicated. However, let's notice some things about this, or something, actually a couple of things. Let's notice some things about this function. As x gets bigger, the quantity in the parentheses is increasing. You have 12 plus 48x squared. Even if you neglect 16x to the 4, 12 plus 48x squared is getting bigger as x gets bigger, so that's increasing. Plus 16x to the 4. 16x to the 4 is increasing itself, so you're adding increasing quantities together. The stuff in the parentheses is increasing. E to the x squared. E to the x squared. Look at the exponent, x squared. As x gets bigger, x squared gets bigger. So as x squared gets bigger, e to the x squared gets bigger. This is increasing. This factor is increasing. The factor e to the x squared is increasing. So the entire quantity, the absolute value of the fourth derivative, is increasing on the interval from 0 to 1. So if we want a value of k, now we have an increasing function. We have an increasing function. Let me see if I can put a little quick graph to illustrate that. On the interval from 0 to 1, we have an increasing function. Increasing function. So the maximum value has to occur at 1, at the right-hand endpoint. So the absolute value of my fourth derivative then is no bigger than 12 plus 48 times the right-hand endpoint, x equals 1 squared, plus 16 times 1 to the fourth times e to the 1 squared. Sorry, I put my graph right in our way here. All I did is I put the right-hand limit of integration into that right-hand expression because that's the biggest it ever gets. And that's my value of k. So if you add up the stuff in the parentheses, you get 76. So k equals 76 times e, the base of the natural logarithm. Okay, so finally, let's finish the problem. The magnitude of error using Simpson's rule then is no bigger than k, 76e, b minus a, 1 minus 0 to the fifth, over 180 times, in our case, n was 10, fourth, and this turns out to be approximately 0.000115. So we have about 3 decimal places of accuracy. Okay, and finally, this ends section 7.7. We just finished 7.7 part 2, where we study error analysis. Feel free to dig into homework on the entire section 7.7, and I'm looking forward to talking again with you guys soon. Bye.